This is lesson 24 of the Quantum Mechanics, a mini lecture series. So throughout the 1920s, there was the question of what an atom is continued. There was a lot of confusion about the very nature of what an atom is. June 1927, to continue our story, Niels Bohr met a PhD student in theoretical physics in Germany named Werner Heisenberg. At the University of Munich. And Bohr actually gave a lecture at the university, and Heisenberg actually rose to make an objection after the lecture. And at the end of the lecture, Bohr actually invited Heisenberg to walk over a certain mountain nearby to talk about things like atoms. And Heisenberg actually pondered on the nature of the atom, and he hated the idea of these imaginary electron orbits in Bohr's model. Okay, so he had like a nucleus and these orbits, and they could never be observed, right? So Heisenberg wanted to work out a connection between the four quantum numbers, if you remember, n, k, m, and s, where n is the size of the orbit, k is the shape of the orbit, m is the direction in which the orbit is pointing, and s is the possible spin state of the electron, so plus or minus a half. So we wanted to connect these with the experimentally determined frequencies and intensities. So frequencies and intensities, okay, aka brightness of the light spectra being observed in the lab. We wanted to make these connections. This connection. So starting point, he treated the atom not as this mini solar system, but rather as like an oscillator, okay, plus, minus, that can produce all the frequencies of the spectrum, okay? And at very large orbits out from the nucleus, the atom will behave like a simple linear oscillator, okay, where the orbital frequency will be equal to the radiation frequency, okay, the observed frequency, the observed color. Okay, linear oscillator in the sense that it vibrates back and forth. Now, from classical physics, the starting point for Heisenberg was classical physics, okay? So from classical physics, we know things like linear momentum, which is just given the symbol P, momentum, in other words, mass times velocity, and displacement from equilibrium. Okay, how far you are from your starting point, in other words. It's given the symbol Q. Okay, if you think back to waves, displacement versus time, let's say displacement is how far the wave is from the resting starting point. So he then would write an equation of motion using these two quantities, P and Q, to work out the energy of the atom, the particle, in state n. Okay, some state n. And he could then work out the quantized values of the energies. And so he actually worked it out. He extrapolated inside the atom, so he went from the outermost orbit, okay, where the linear momentum comes to play, and he worked his way in. That's what extrapolate means. Worked his way into the atom. Now, classically, we know that P times Q is the same thing as Q times P. Okay, this is called the commutative law. Commutative law for multiplication. Okay, it doesn't matter which order you multiply two things, you'll get the same result if you swap them around. Oops. But in quantum mechanics, this isn't necessarily the case. Okay, and he included a quantum postulate, okay? So he supposed that PQ minus QP isn't in fact equal to 0. Okay, so for example here, suppose you've got 6 times 3, that's 18. Well, 3 times 6 is also 18. So classically, 18 minus 18 is 0, right? If you do take this to be 18, that 18, if you take the 18 over, 18 minus 18 from algebra, this is 0, rearranging this equation. But he actually proposed that PQ minus QP is in fact h over 2 pi times I, where I is just the square root of -1. Okay, it's called an imaginary number. Imaginary number, that's I. H over 2 pi, remember that comes from the quantum postulate for things like angular momentum. And so therefore the energy states of an atom are quantized and they're time independent. What does that mean? It means that they are stationary, as is the case in Bohr's atom. And Heisenberg actually called this a gift from heaven, okay?